So what I want to start talking about, so we're going to be doing a bunch of problems where the directions will be prove or show. Whoa, man, that's way too thick. So prove or show whether the series converges or diverges. Um, when we're doing the more advanced ones that we're going to start with today and that we were doing with the integral test last week, if the series converges, we know there is a sum, but we don't necessarily know how to find it exactly. And so you can approximate the sum pretty easily using a computer because the limit of the sequence has to be 0. So like once you start adding 100 terms or something like that, the thing that you're adding is getting so close to 0 that you're not changing the decimal by much, or you're not changing the display on a calculator very much. So you can approximate using a computer. But the point of the proofs now is just to prove that there is a sum, or if it diverges, prove there's not a sum. If there is a sum, we could approximate using a computer, but we couldn't get an exact sum in most cases. And so I want to kind of review what we've talked about so far. So, or at least the two big results that we've got, two biggest results we've got so far. So we've got geometric series, and then from the integral test, when you guys were working the homework, you ended up proving what P series did. And so geometric series, we know, are series that look like this. So the sum k equals 0 to infinity of a r to the k. And then a P series is the sum k equals 1 to infinity of 1 over k to the p. And so these two series are kind of the two basic types of series that we try to break most other series down into. Geometric series are significant in that k is where on a geometric series, or if you're using the letter n, where does n or where does k show up on a geometric series? What makes it geometric? What do you guys think? So k is in the exponent. Okay, so k is in the exponent on a geometric series. That's so you have like 2 to the k or 3/4 to the k or something like that. On a P series, k is in the base. So geometric series cover all exponential functions. P series cover all power functions. That's why it's called a P series, a power series. So geometric series we know converge if the absolute value of r is less than 1, and we know they diverge if the absolute value of r is greater than or equal to 1. We know that P series converge if P is greater than 1. So that's something that you go through. We went through on the homework for the integral test. The main point of the integral test now is to prove that that's the case. These diverge otherwise. And so they diverge if P is less than or equal to 1. And so that makes a lot of problems doable. Any power function, any exponential function, or anything that could be broken down into that can be proven using those two results. So let's just go through a couple quick ones. So number one is just the sum k equals 0 to infinity of 1 over 3 to the k. And number two is going to be the sum k equals 1 to infinity of 1 over k to the third. And so the first one, what type of series is that? Is that geometric? Is that P series, or is that something more complicated?
Geometric.
Also,
geometric. Go ahead.
Pull up just one line, please.
Yep.
Thank you.
Yeah, no problem. So the first one's geometric series because you can rewrite this as the sum k equals 0 to infinity of 1/3 to the k. So our quick proof is that, okay, this converges. We know that it converges because it's a geometric series. The absolute value of r is 1/3. And then what's significant about that is that it's less than 1. Does that make sense to everybody? That's good. All right, we can find the sum on a geometric series. We won't. We did that before. We're not going to do that right now. We're not going to focus on how to find the sum, but we could do that. On number two, we're going to say this converges We know that it converges because it's what type of series? Is this a geometric? Is this a P series, or is this something else?
P series.
P series.
P series. So we say that it's a P series. We say P is equal to 3. And then what's important on a P series? So on a geometric series, it's important whether the absolute value of R is bigger or smaller than 1. What's important on a P series? Whether P is bigger than 0, whether P is a fraction, what do we want to know?
P is bigger than 1.
P is bigger than 1. So P equals 3, which is bigger than 1. That's the condition that makes it converge. This is one where it would take more advanced methods to get an exact sum. I think we could probably do it for 1 over k to the third, but much more complicated than that. You actually cannot do it exactly. All right, any questions on this so far? We're good? All right. So number 3. Real quick. So if I have the sum k equals 3 to infinity of 1 over the square root of k. So, okay, so is that a P series? Is that a geometric series, or is it something else?
P series.
This is a P series, so we can rewrite this as the sum k equals 3 to infinity of 1 over k to the 1/2. This is, again, it's a P series. P is 1/2 this time. That's less than 1, so that means that the sum diverges. It's going to go to infinity in this case. But this diverges, and so there's no sum defined anyway. Okay, any questions so far at all? You guys good? Okay, so what I want to go into is more complicated series. And so directions on the standard problems are going to continue to be prove whether the series converges or diverges. But I want to talk for a minute about series with all positive terms. And so we talked about this when we were dealing with the integral test. And when we say all positive terms, we mean for large K. So it might even be that some of the early terms are negative. That doesn't matter as long as eventually all of the terms are positive. And the significant thing about that is that if the series diverges, do we remember last week what we said was the only way for that to happen if you're adding all positive numbers? What's the only way for a series to diverge if it has all positive terms? What do you guys think?
Harmonic series?
The harmonic series would be one that has all positive terms and diverges. But what I mean is, how does it diverge? Why does it diverge? Because the sum goes to infinity, goes to negative infinity, bounces back and forth. Which of those are possibilities when you're talking about all positive?
Just to infinity.
Just to infinity. Does that make sense to everybody? So if the series diverges, then it goes to infinity. Obviously, if you're adding all positive numbers, there's no way for it to go to negative infinity because you have to add negative numbers for that to happen. Why could the sum not do something like this? Like, why could we not go 5, 7, 5, 7, 5, 7, where we're bouncing between those two numbers? Because those are all positive. Why is it that if you're adding positive numbers, you cannot get sums that alternate between 5 and 7?
Because in order to go from 7 to 5, we'd have to add a -2.
That's exactly right. So to go from 7 to 5, you'd have to add in a -2. And so when we say the series has all positive terms, we don't mean the partial sums are the only thing that's all positive. We mean the thing that you're adding is all positive. So you can't drop ever. The sum is always going to be increasing. Does that make sense to everybody? Okay, so that's significant because then we can make conclusions based on simpler series when we're talking about more complicated ones. So like if we think graphically, so what's going to happen is we're going to have like a more complicated series that we're dealing with. And what we're going to try to do is we're going to break it down into one of these two. We're going to compare it to either a geometric series or a P series when we can. And so let's say, for instance, that you have this easy series and the series diverges. Okay, so again, it's a series with all positive terms. The easier series, let's say, diverges. So then graphically, we can think of it as being like that. Does that make sense? So we think of it as increasing to infinity if it diverges. So let's say that I could prove to you that the original series So the harder series is smaller than the easy series. Could you tell, knowing that, whether the original series, the harder one, converges or diverges? So like if it's always smaller than that black line, if I draw in a blue line, could I draw it where it's always smaller than that and still make it diverge? Is that possible?
No.
Well, if it's smaller, I could make it go to infinity. It just goes to infinity slower. Does that make sense? Could I make it converge by doing that? Sure, I could make it go up and then converge like that. So if the original series, the harder series that we're going to be talking about, is smaller than one that's divergent, that's not helpful because it could converge or it could diverge. What if instead I could prove to you that the original series is bigger than the easy series? So if I could prove that the original series is bigger than the easy one, then what would it have to do if it's always above this?
Go to infinity.
Has to go to infinity as well. So if the easy series diverges, so if the easy series, if the easy one diverges and the original is bigger, then the original diverges. Does that make sense from that picture? Everybody get the idea? Okay, now let's make another picture and we'll talk about it being in red. I don't want to do that. All right. And so let's say now the easy series converges. Okay, so if the easy series converges, but what you're adding is all positive terms, because you're adding all positive terms, it's always, the sums are always getting bigger and bigger and bigger, but they level off if it converges. So if the easy one converges, okay, let's say I could prove that the original series again is bigger. If the original series is bigger than that, so if it's up here, could the original series, could the harder one still converge if it's above the easier one?
It could.
It could, because it could level off like that. Could it diverge by going to infinity?
It could.
Yeah, because it could just turn and go up. And so if in that case, if the easy one converges, if the easy one converges, it's not helpful when the original series is bigger than that. But if the original series is smaller than that, let's make this fix. If the original series is smaller than that, then why would it have to converge? So first of all, if it's smaller than that, I cannot make it go to infinity. Is everybody clear why? So it's got to stay under that. So why would it have to level off? Why can't it go to negative infinity? Like, why can't I have it do that?
It's all positive terms.
It's all positive terms. Why can't I have it bounce? Again, all positive terms. So if it's not going to do that, if the only way it can diverge is by going to infinity, it can't go to infinity. So if it's smaller, then it also converges. So if the easy one converges and the original is smaller, then the original converges. Okay, so let's see how that works in an example.
Wait, why would, like, if it bounces,
Yeah.
well, like it bounced from 5 to 7, 5 to 7, and those are all positive?
The partial sums would be all positive, Max, but to go from a partial sum of 7 to a partial sum of 5, you would have to add a -2. So it's not just that the sums have to be positive, it's that all the things that you're adding have to be positive.
Okay.
Does that make sense? Okay, but what you're saying is also the reason why, if it's not a series with all positive terms, then these conclusions are not correct. Does that make sense?
Yeah.
If it is all positive terms, then this is right.
Okay.
All right. So directions again are just prove whether the series converges or diverges. All right, and so here's what we're going to do. All right, I don't know what number we're on. I think number 4. All right. So if we've got the sum, let's say k equals 1 to infinity of k to the second minus 8k plus 1 over k to the 4th plus 6. Okay. Okay, so what we're going to do on this, and what I would recommend is that you kind of watch this and then copy it down and kind of think through what we're doing. But your call. When you look at this problem, obviously this is more complicated than what we've done before. So the kind of the general process should now be, first of all, is this a geometric series? No. Now, is it a P series? No. So then, okay, would the K-term test work? And so somebody remind us what the K-term test says again real quick. So if the sequence
converges to 0, then the series will be shoot.
You're right. If the sequence doesn't go to 0, then the series diverges. Does that make sense? Okay, so if the sequence does not go to 0, then the series diverges. The sequence here, why does the sequence go to 0? In this case, not the series, but the sequence.
K squared over k to the 4th.
K squared over k to the 4th. Does that make sense to everybody? Okay, but if that sequence went, like it was k to the 4th over k to the 4th, then the sequence would go to 1 and we'd say, okay, diverges by the K-term test. Okay, and then the integral test is going to be something we're going to try to avoid for the most part. And so what we're going to do when we see a series like this, if you remember back to when we were doing sequence proofs, when you have ones with all of the same types of terms on the top and bottom. So here you've got all power functions on the top, all power functions on the bottom. The way we're going to start this is we're going to say, okay, compare to an easier series. So the sum k squared over k to the 4th. And what we're going to do is we're going to pick the biggest thing on top and the biggest thing on bottom. Does that make sense? Okay, we're going to simplify that and prove what that does. So k squared over k to the 4th becomes 1 over k squared. What does that series do? Does that series converge or diverge?
Converge to 0.
It converges, not necessarily to 0, but it converges, the series does, because it's a P series where P is 2, which is bigger than 1. The sequence goes to 0, but the sum would not. Does that make sense? Everybody clear so far? Okay, so graphically, we can think of this as being a sum that does this. First of all, is this a series with all positive terms? I guess we should have said that to begin with, other than we were talking about that. So it does have, yeah, for large K, this has all positive terms. And we know that because the biggest term on top is K squared, which outpaces the negative 8K and the plus 1. So for large K, the top is positive. For large K, the bottom is positive. So this is all positive. So then that means that when the 1 over K squared converges, the graphic looks like the blue one I've got up on the top right. And so it increases, but it levels off. So, okay, in order for this idea up here to work, do we want the original series to be smaller than 1 over K squared, or do we want the original series to be larger than 1 over K squared?
Larger.
Smaller.
Oh, wait, the original, yeah.
You're good. We want the original to be smaller than the easy one. And I think you were just saying it backward, Devin. Does that make sense? Okay, so we want the original to be like down here because then it would have to level off. Okay, so let's think through why it is. And so we're going to prove that, and we're going to say, okay, K squared minus 8K plus 1 over K to the 4th plus 6. I'm going to say that that is less than K squared over K to the 4th plus 6 first. Why would that logic be correct? What's the difference? So that on those two fractions, the bottom is the same, and what's the difference in the numerators? which one has a smaller numerator?
The one on the left.
The one on the left has a smaller numerator. How do we know that? How do we know that k squared minus 8k plus 1 is smaller than k squared?
Because it have the extra minus 8k on the left.
Because you're subtracting 8k. And so 8k is bigger than 1, so the top is smaller on the first fraction there than the top is on the second fraction. Does that make sense to everybody? Okay, in turn, that is less than k squared over k to the fourth. How do I know for sure that that's true? So the numerators are the same, but this denominator, the first denominator, is bigger than the second denominator. Why does that mean a smaller fraction? So that's like if I said 3 over 10 versus 3 over 4. Which of those is a smaller fraction, 3/4 or 3/10?
3/10 is smaller.
3/10 is smaller. So same idea with the k's. Harder to think about with the k ones, but the same idea. Does that make sense? Is everybody clear so far? Okay, now what that means is that the original series is smaller than 1 over k squared. 1 over k squared converges. What does that mean the original one does?
Converges.
It converges if they're all positive. And so are they all positive here? We already said they are. We need to explain that. And so we put this. And so it looks kind of like the squeeze theorem, and it's a similar idea to the squeeze theorem, but not exactly the same thing as the squeeze theorem. But this 0 is less than that is necessary, because if that weren't true, maybe the original would go to negative infinity, or maybe it would bounce like sine or cosine would. Does that make sense to everybody? Okay, so that's your proof that the original series converges. And so we're going to make a conclusion down here. We're going to say, so the original series, the sum k squared minus 8k plus 1 over k to the fourth plus 6 converges. And this is called the direct comparison test. Does that make sense to everybody? Any questions on what we're doing? All right. So I want to look at another one, and then I want to talk about how some of this can switch. Okay, so let's go through another problem. Okay, so if we've got the sum from 4 to infinity of 5k plus 7 over 8k squared minus 3k. All right, so we just kind of go through the rundown. We first say, okay, is this geometric? No. Is this a p-series? No. Does the k-term test work? No, because the sequence does go to 0. Does that make sense? Okay, and then we say, okay, this is a series that has all positive terms, or at least for large k, it has all positive terms. And that's because the largest thing on top, largest thing on bottom are both positive. All of the function types are the same. So everything that's there, the 5k, the 7, 8k squared, and 3k, those are all power functions. So we're going to compare this to the sum 5k over 8k squared. And we're going to figure out what that does. Does that make sense? Questions? Okay, we're going to simplify that. We're going to pull the 5/8 out. And then k divided by k squared is the same thing as 1 over k. So we're going to rewrite it as 5/8 times the sum 1 over k. We're going to say, okay, this series over here diverges. And our rationale is that it's a constant multiple of the harmonic series. Or you could say it's a constant multiple of a P series where P is 1. Questions to there? You guys good? Okay, so what we should now be thinking is that this one on the right diverges, and because it's all positive, that means graphically it looks like that. So would I want the original series to be larger, or would I want the original series to be smaller in order to make an easy conclusion?
Larger.
I want it to be bigger because then it would have to go to infinity. Okay, so based on the numerator, it is bigger because 5k plus 7 is bigger than 5k. And we can keep the bottom the same. In turn, that's bigger than 5k over 8k squared because the denominator of the middle fraction, the denominator is smaller than the denominator of the one on the right. A smaller denominator is a larger fraction if everything's positive. Does that make sense? For all of this logic to work, everything has to be positive. It's all contingent on diverge means infinity, which isn't always true, but is true when we talk about all positive. And so we say, okay, the smaller one is bigger than 0, therefore the bigger one is bigger than 0. Does that make sense? And so then the original series diverges by direct comparison. Any questions at all?
So what if it's going to negative infinity? Do we just reverse the process?
So Devin, let's say, so this works when everything is positive. So negative infinity would not be a possibility.
Okay.
If everything is negative, you could take a -1 out, kind of like the 5/8 here, and
Oh, I see.
do this. Does that make
Okay.
sense? You would
Yeah.
make everything positive. Now, if the sequence is alternating, this does not work.
Yeah, it doesn't work then.
But this would work for series that are all negative if you just pull a -1 out.
Okay, cool.
Does that make sense? Okay. Does that make sense to everybody? That's actually a really good question. Does everybody follow that? Now, if it's alternating, this wouldn't work at all. But if it's all positive, this does work. If it's all negative, that you can quickly make all positive by just factoring a -1 out. Okay, other questions? Okay, so a couple of quick things to notice when you're looking at the two proofs. So one is when I'm writing that or that, just as far as what we'll do in this class, if you use the word series to refer to a series in the problem, we will assume you mean the original problem unless you specify otherwise. Does that make sense? So, okay, so here we've got kind of like two different series going on. When you refer to the word series, I'll assume you mean the original one unless you tell me you're talking about something else. Okay, another thing is that it's whatever this series does that is going to determine the answer. So if the easier one converges, the original one is going to converge whether or not this inequality is true. So if the inequality is true, you use direct comparison. If the inequality is false, you will use something called limit comparison, but the conclusion will still be whatever happened over here. Does that make sense? So limit comparison is going to be a different way to prove the same result. So if it's one like this, where it's all power functions, or here in a minute, if it's all exponential functions, whatever this easy series on the right does, that is what the original series will do. So if the easy series converges, the original one for sure converges. If the easy series diverges, the original series for sure diverges. If the inequality is the way you want it, so if you want it to be smaller and it is, or if you want it to be bigger and it is, you can use direct comparison. If it's not the way you want it, then you use something called the limit comparison test, which we'll talk about in a few minutes. Okay,
So-
go ahead.
Before, in the conclusion part, when you left out the k equals 1 to infinity, we're allowed to.
I'm okay with that. So
Okay.
if you and you'll notice I'm not putting these like k equals 1 to infinity, all of them, assuming we're talking about an infinite sum. And the reason that's not as important is because where you start does not affect whether or not it converges. It would affect the actual sum. Does that make sense, Max? So when we talk about power series later, it's important. When we were doing geometric series and we were finding the sum, it's important, but it's not as important when we're just proving whether or not there is a sum.
Okay, awesome. Thank you.
Yeah, no problem. Other questions? You guys are good? Okay, so I want to go to another example.